All right, here we go. I'm recording. Here we go. Mark from Jeter Tutors, refreshed by that run. I just ran for an hour, and now my mind is clearer. So again, my channel is geared toward just focusing on specific things that students I've tutored are having problems with currently, so that they can go to this site, refer to it, and get A's on their quizzes and tests. So let's focus not so much on the theory of resonance structures. Just let's assume that there are molecules that have two or three different kind of configurations. Okay, the way that the bonds, if you have double bonds or single bonds, the way everything is organized. So the first rule to determine whether or not a resonance structure is most stable is using the octet rule. So if all of the atoms in the molecule have fulfilled or satisfied the octet rule, then it's more stable and it is more prevalent in the resonance. So there's going to be more chance and probability wise of it looking like that configuration than another configuration where the atoms don't satisfy the octet rule. So that's the first thing. And you can stop there. Okay, now if you have two molecules where all the atoms satisfy the octet rule, okay, but the formal charges they look different, right? So then what you do is you look at the formal charges on each atom. Okay, now if there are more atoms with more charge, they're less stable. Okay, if there are less atoms with charges, and also if the charge integer value is lower, as in -1 is less than 0, or say -2 is less than -1, and of course -1 is less than +1. So if it's a lower number, okay, then you have a more stable, less energetic molecule. So in general, in nature, things that have more energy are more unstable. Okay, if you take anything like this bowl of fruit, and I'm just holding it, right? And if I just start moving it around, there's more chance of things falling out. You know what I'm saying? So that's a good example. I probably need a banana. Let's see here. Am I breaking a YouTube rule by eating? Because I just ran for an hour. Good. Woohoo! All right. Okay. Now, if the formal charges, are, there's no say one is -1 and one is -1, and you can't tell the difference. Then you look at where. So then you look at the atom's electronegativity. So wherever the formal charge is, because assuming that everything is equal, say it's oxygen. Okay, so the formal charge on oxygen is, say, -1. Okay, and say that the formal charge on a different configuration is on the carbon. So when you look at the periodic table, and I'm assuming that you guys know Lewis dot structures, I'm assuming you know formal charge, I'm assuming you know about electronegativity trends. Okay, if you go from, well, let me see. Yeah, I guess it'll come up like this. So if you go from left to right on the table, okay, the atom sizes get smaller. So atomic radius goes down. Remember, atomic radius goes down. So fluorine is like a little p, and sodium is like a big tennis ball, right? And the reason why the atomic size goes down is because the electronegativity goes up. In other words, everything is pulled in more. Okay, pause, think about that. Selah. As you go left to right in any group, okay, you are going to, or wait, it's a period or group. In any period, excuse me, left to right in any period, then you're going to increase in protons, right? So you got one more proton and it changes the element, right? So you got your boron and your nitrogen, your oxygen, your carbon, your oxygen, nitrogen, sulfur, fluorine, chlorine, all the ones all the way over there, right? the number of protons, what it does is increase the overall positive charge in the nucleus, which attracts the electrons. Okay, so that attractive addition of a proton actually outweighs the negative charge. I mean, the negative contribution, like proportionally. Okay, so it pulls down the electron cloud. Okay, now electronegativity is a measure of how much that pull is. So simply said, when you have everything with good with the octet, everything is same with formal charge, you look at the electronegativity of the atom versus with the formal charge versus the other resonance structure, and whichever atom has more electronegativity is the more stable one. Okay? Because if you have a negative charge on a very high electronegative atom, then it's going to be more stable than if you have like a positive charge on an electronegative atom. So, okay, so say you have like a positive charge on a really weakly electronegative, something that has a low electronegativity, and you have a positive charge on something that has a really high electronegativity. Well, the positive charge on the one where it's the low electronegativity is it's gonna favor that more. So in that case, the atom with the lower electronegativity is going to win for stability. Okay, so that's clear as mud. But let's look at some examples. Okay, so CO3, NO3, SO3, etc. All of these have what are called equivalent, okay, structures. So you can have carbon, you can have your oxygens, right? Now carbon has 4 bonds to give, right? So if I have this, now if you remember your Lewis dot structures, I've given 1 electron from the oxygen, and I've got 6 to give. 2, 3, 4, 5, 6. But we know that we can't just, oh my gosh, I have to make that darker. 1, 2, 3, 4, 6. But I know I can't just have a lone electron out there. So I need to pair it. Now that I've made that 7 electrons, it satisfies the octet rule because there's a shared 2 here. So you have 2, 4, 6, 8. But because I needed to add this one, there's a negative charge on there. Okay. Now for the double bond, I've got 2. I've given 2 to make the double bond with the carbon. 3, 4, 5, 6. Sorry, 2. Yeah. So that's 6. So I don't need any charge. And there's an octet rule satisfied because the shared electrons count. So I have 2, 4, 5, 6, 7, 8. And here this oxygen is the same. 1, 2, 3, 4, 5, 6. But I need to add that so I can satisfy the octet rule and I make it a negative charge. Okay, so I can have this configuration. Okay, you can also you can change it around where this carbon has the charge on it. So these two, or you can change it where this one has it. Okay. So basically though, since oxygen, the formal charge on this polyatomic ion is -2, right? Oh, but 2 negative or -2, because -1 and -1, and then this is 0 because that's 2, 4, 6, 8, and I have 4 electrons, right? And carbon to give. The overall charge is -2, but the resonance structures are equivalent, and because the formal charges are on the same atom, oxygen, I'm not really comparing anything, so I pretty much, structures, and they're all equally contributing. Okay. Now this is the same is true for NO3. Let's kind of write it like this. So we'll have a minus here, and yeah, excuse me, you'll have 1, 2, 3, 4, 5, 6. Minus here, you have 2, 3, 4, 6, 8. In my mind, when I'm saying 6, 8, and all that, what I'm counting is I'm counting the valence electrons that oxygen actually has to give. Now, just let me say this: there's electrons everywhere to give or transfer, around. I'm gonna make these dots thicker, right? So it's nothing for an element to just grab an extra electron. If you want to prove it, I mean, you can just take a balloon and rub it on your head and then stick it. You've charged that balloon, okay? So you've transferred electrons, I think, from you to the balloon, and the wall is positive and the balloon's negative and it sticks, or one of those two. So, but you're moving electrons around it all the time. Now this one is stable. 1, 2, 3, 4, 5, 6, 7, 8, right? But you could also do the same thing. You could change it around, okay? Now, okay, so anything like this is going to be equivalent structures because everybody's octet rules is satisfied. The formal charges are the same, okay? And the atoms that the formal charges are on are the same, okay? So they all contribute, you could say 33.33% equally. Now let's take something like carbon. I think this is cyanide, okay? I think CNS is cyanide, really deadly, right? So 1, 2, 3, 4 bonds, carbon is given. So nitrogen has, I think, 5 to give. So 1, 2, 3, 4, 5. But then we have 5 here, right? I've done that, right? So, but I have 2, 4, 6, 8. So I'm good. I'm good on that. I don't have to add like a charge, okay? So sulfur, it has 3 to give. So 1, 2, 3. So now here's the thing. 2, 4, I think it's got more than that. Wait a minute. Skirt. So we're going to have, is that 3 to give? Sulfur is schnapps. I believe it's under, I think it's got 5. 1, 2, 3, 4, 5, 6, 7, 8. I think it's negative. Okay. So I hope that's right. If it's wrong, you can leave a comment below. So we can have carbon that has triple bonded with nitrogen. Okay. You can have carbon that is double bonded to nitrogen and double bonded to your sulfur. So I've got 1, 2, 3, 4, 5. Okay. And then I have to add that extra electron. So 2, 4. I'm adding the extra electron and complete the octet rule. So now I've given 2, 4, 6, 8. Yeah. So this is going to be 2, 4, 6, 8. And then this is going to also be, wait a minute. If I added a periodic table, shoot. Hold on. That's a live broadcast. It kind of sucks. I need my periodic table. It's sort of like having your dictionary. So if you've encountered this, don't worry. I'm just like you. Okay. Come on. Give me periodic table. Okay, so let's just, while we're waiting for that to come up, let's put the other resonance structure here. Okay. Which is kind of a crazy one. Right? And actually, I don't know if that's possible. I think it's this. Okay, so let's, I can't have a double bond. So we have a positive charge here because we have an extra electron when we're not, basically we have 2, 4, 6, we have 7, 2, 4, 6, and you have that extra electron. You have a positive charge to balance that out. Okay, let me get that. Okay. Where was it? Where was it? Here it is. Okay, no, that's not right. So it was triple bonded S. Okay, so you have triple bonded N, triple bonded S, single bond here. Okay, and the charge on carbon is 0. The charge on carbon is 0. Now the formal charge on nitrogen here with the triple bond is going to be 0. Okay, because I need 1, 2, 3, 4, 5. The formal charge on sulfur here is actually 0, so that tells me something. That tells me that it's that it's 1, 2, 3, 4, 5, 6, 7, 8. So that tells me that there was 4, 5, 6. Yeah, 6 electrons, valence electrons for sulfur. Okay, so here we had to add an extra one. So we had 1, 2, 3, 4, 5, 6. We have to add it so it makes it negative. Okay, sorry. Yeah, negative 1. And then this, we would use 2, 4, 6, and then 6, right? And then we had to have we have to have 7, 8. Okay, so 1, 2, 3, 4, 5, and then 1, 2, 3. To me, yeah, for each bond, 1, 2, 3, 4, 5, and we have a positive charge on here. Okay, because now we have 1 less electron, but we still have 8. Okay, so we're not going to keep adding electrons because we have 8. We satisfied it. We can't add another one to make it 6, right? We just have to have 1 less electron in the valence. Okay, so now let's go to this one. Nitrogen has a formal charge of -2 because they got 1, 2, 3, 4, 5. Okay, and then I got 5, and then I need 6, 7 here to make 8. 2, 4, 6, 8. So it's -2. Okay, so now I've got -2, 0, and then the double bonded has a formal charge of 1, 2, 3, 4, 5, and then I need another one, so that's -1. Carbon has 0. So let's look at nitrogens. -2, 0, -1. Well, the more stable one is going, and then actually if you look at the entire molecule here, this one has a formal charge of -1. This one has a formal charge of -1. This one has a formal charge of -1. But there are more formal charges on more atoms. So this is least stable. Now you know why I had to go for a run. Okay. Now that's if you look at all these, all of them satisfy the octet rule. So that's why we went to formal charge. So all of them satisfy the octet rule, but now this is the least stable. Now we can compare these two, okay, nitrogen and sulfur. Let me just quickly pull up my periodic table, okay, and it looks like nitrogen is 7 and sulfur is underneath oxygen. This goes like this: nitrogen, oxygen, sulfur. So if you look at electronegativity, electronegativity increases as you go to the right. So sulfur has a higher electronegativity than nitrogen. Okay, so now let's go back to that electronegativity rule. What we were saying is that if you have a high an atom with a high electronegativity and it has a negative charge on it, then it's going to be the more stable, because that's better for that. Okay, nitrogen is electronegative. It's higher than most. You know, it's kind of in the middle, but it's got a smaller electronegativity than sulfur. So least stable, most stable, and the first loser, second place, is the one down here. So I would say mid-stable, right? So third, Olympics are coming up. First, second, right? So I shouldn't say first loser. I know lots of people who have silver medals, and that is an awesome achievement. So I take nothing away from that, because I didn't even make the Olympics. All right, so shout out to John Coyle, yes, silver medalist. That's pretty much it. So a quick review is, without getting bogged down in the details, number 1, octet. Number 2, formal charges. Right? Number 3, electronegativity. Okay? So review this, and if you look down in the comments, there's a link to a paper that Dr. Peggy Kline did in 2000 and at Santa Monica College, and it's a great little, you know, HTML file that you can pull up, and it has some examples in there too. All right, this is Mark from Jeter Tutors. I hope this was not too confusing, but if you follow these 3 rules in this hierarchy, then you can determine which molecule, resonant molecule, is most stable and which is least stable. All right, till next time.